In the last session related to static inventory problem under risk, if you recollect, we have referred to the benefit analysis. Now, obviously, if there is a benefit analysis when the sales of the product is involved, related to the production of an item within a manufacturing system, and when the cost based analysis is needed, what is important is that related to type 1 problem, or for that matter any type of problem, you must go for cost analysis. So, during this session, three specific issues we will be discussing. First one is the type 1 problem and why cost analysis is needed for type 1 problem. We will highlight this case and with a numerical example, and then we will refer to type 2 problem, and the type 2 problem also we will discuss with a numerical example. So, for the next half an hour or so, this will be our coverage. Now, so let us talk about type 1 problem. Already we have stated what is a type 1 problem. When the demand is a variable and the lead time is constant. So, this is just one combination, and we will be dealing with the cost analysis. Now, the certain points you should keep in mind. Now, the cost analysis is relevant when inventory items are intended for internal use, mainly for production purpose. As we have been mentioning all the time, that the kinds of activities which you carry out within the production systems, within the manufacturing systems, all these activities are having a bearing on the cost. So, those are basically the cost related activities. So, whenever the inventory items are intended for internal use, like for example, say inside supply case, you know what is an inside supply case. So, obviously, you must go for cost analysis. That means, if once you have the cost equation, you establish the cost equation and you determine the order quantity in such a way that the total relevant cost is held at the minimum level. So, we need to minimize the total relevant cost against the order quantity. And why I am saying total relevant cost? Because if you go through a particular problem, you will come to know that there are certain cost elements which are referred to, whereas there could be many other cost elements which may not be relevant or with respect to a given problem. That is why you need to identify only those cost elements which are referred to as relevant. So, what you need to do once you identify these cost elements, the total relevant cost equation you have to establish. So, expected cost is determined considering ordering cost, purchase cost, stock out cost and the salvage value. We have already referred to all these different types of cost elements, like we have defined what is order cost. So, you are placing an order, it is a static inventory problem, and that is why say one order is placed, single order. So, for placing an order you must incur certain cost. So, that is referred to as the ordering cost. Normally, this is estimated per order basis. Then you have the purchase cost. That means the purchase, the price or say the production cost per unit must be known. So, this cost element also you must consider. Then we have stock out cost, and we also have the salvage value. That means the unused items, what do you do with the expiry of its use with the expiry of the time or the order or say of the season, what you do, you need to, you can to what extent you can the salvage its value. That means can you dispose it off with a reduced price. So, this is referred to as the salvage value. So, these four types of cost elements you need to consider. So, what will be the expected cost expression, that is given as EC. So, this is given by C plus PQ. So, C is the ordering cost, the PQ, that means Q is the ordering quantity and P is the purchase price. So, P into Q will be the total purchase cost, and capital A is per unit stock out cost, and M minus Q FMDM. So, what is M? M is the demand and Q. So, M minus Q is basically the demand is more and the order quantity is less. So, this M may vary from Q to infinity. So, this is a stock out case. So, this is the expected number of stock out units. So, M minus Q in FM DM. So, what is FM? FM is against a particular demand M, what is probability density function. Now, this is the cost, this is added, that is why it is positive. Now, the certain the quantities which are considered to be excess, okay, after the expiry of the selling season, or what may be considered to be excess, and these excess amount you can sell with a reduced price. That is why it is referred to as the salvage value. So, salvage value per unit is given as capital V, and this is the excess amount, that means the order quantity Q minus M. That means when the the actual demand varies between 0 and Q. So, obviously, this is the excess amount. So, Q minus M FMDM. So, expected number of units excess. So, this is the total expression. We have simplified these expressions. We have after doing manipulations, we have these expressions C plus PQ plus A minus V integration Q to infinity M minus Q FMDM plus V into M bar minus Q. So, this is the average demand. Okay. So, this is the expression. Then what do you do? Obviously, you determine the order quantity Q in such a way such that the expected cost is minimum. So, for minimization of EC, what you do? You take the partial derivative with respect to Q, del Q of EC, and set it equals to 0. So, this is the fulfillment of necessary condition. So, ultimately what you get? You get probability that M greater than Q. That means, this is the probability of stock out. So, what is the expression for the optimum stock out probability? That is P minus V divided by A minus V. So, I suggest that you take the partial derivative with the expected cost expression, set it equals to 0, and you carry out the exercise, so that ultimately you get these expressions. So, this is the defining relationship which is referred to as the optimal stock out probability. This notation also sometimes used, that is PS. PS stands for probability of stock out. So, the sufficient condition for minimizations, as you already aware of, that is the second derivative, second partial derivative with respect to EC, partial derivative with respect to Q, that is of EC, you will be is positive. So, this is you can also check that whether the sufficient condition for minimization is fulfilled or not. Okay. Now, so once you have established this equation, you know what is the decision variable, and you determine the value of the decision variable in such a way that expected cost is held at minimum level. So, now we can refer to a particular example. So, let me first elaborate what is this numerical example. A large department store has just purchased a new central air conditioning unit. The lifetime of the air conditioner is estimated at 12 years. The manager must decide how many spare compressors to purchase for the unit if he purchases the compressors now. They will cost $100 each. If he purchases them when they fail, the cost will be $1,000 each. The table gives the probability distributions of the number of failures of the part during the life of the air conditioner as supplied by the manufacturer. That means the table they related to the probability distribution of the number of failures. So this table is given to you, and then we have other data. The installation cost of the compressor as well as its salvage value is assumed to be negligible. Okay, so this is the assumptions. Now, what is to be determined? How many compressors should be purchased if the holding cost is neglected? Okay, so this is you need to determine the number of compressors. How many compressors should be purchased now if the holding cost, which is mainly the opportunity cost of the money invested, is 10%. Okay, so as I have already mentioned in the very first week, that there are the different types of the cost you need to consider for inventory analysis or for determining the inventory control policies. So one such the cost is the holding cost, or say inventory carrying cost. So usually the inventory carrying cost is estimated as a percentage of the average inventory which you hold. Okay, so that's why. So here what is mentioned that in this particular problem that the holding cost is 10%, is just 10%, and so it is considered to be reasonable. So 10% holding cost. Assume failures occur at equal intervals. That means the single failure occur at the end of 6th year. That means the total the lifespan of the compressor is 12 years. So if say one failure occurs, we will assume that so the once in 12 years, that means at equal intervals, that means single failure occur at the end of 6th year. If say the two failures occur, they will be occurring at the end of 4th and at the end of 8th year. Okay, so this simple rule we will be following. And if suppose for example there are 3 failures occurring, that means these failures will occur at the end of the 3rd, 6th and 9th year. So these assumptions we are making. Okay, so now this is the table given, that means against the number of failure what is the corresponding probability. So so based on the frequency counts, so we have this data. That means if number of failures is 0, corresponding probability is 0.30. That means 30% of the cases there will be no failure at all. With one failure the probability is 0.4, 2 failures the probability is 0.25, and 3 failures the probability is 0.05. Just 5% of the cases there will be 3 failures. Okay. Now we have added this column. That means the probability of number of failures greater than m. Okay, that means if 0 is for against 0 failure, the probability is 0.30. So the probability that the failure will be greater than 0, obviously it could be 1, 2 or 3. So obviously it is 1 minus 0.3, that means 0.70. Similarly, the probability of number of failures greater than 1, that means it will be 1 minus 0.3 plus 0.4, that means 0.30. And similarly, we calculate that the probability of number of failures greater than 2, this will be 0.05, and the probability of number of failures greater than 3, obviously it will be 0. Okay. So, we have added this column. Please try to understand the meaning of all these values. Okay. Now, with holding cost neglected, the first case we will assume that there is no holding cost, okay, for this particular numerical problem. And in the second case, we will relax this assumption. We will assume that the holding cost is 10%. Okay. So, with holding cost neglected, first case, the cost matrix can be developed as shown in the table. So, this is we have the ordering strategies. Ordering strategy depending on say the how many possible failure levels you have. So, that is referred to as the state of nature. Okay. So, either there could be 0 failure, 1 failure, 2 failures or 3 failures. Okay. And corresponding probability already it is known as given in the table, previous table. So, the ordering strategies could be 0. That means, there will be no ordering for the compressor, or there could be 1 unit ordering or 2 units ordering or 3 units ordering. So, this is all possibilities we have explored. Now, against suppose your ordering strategy is 0 and your the demand is also 0. So, obviously, there is no cost involved. Is it okay? If suppose you do not place any order, but there is one failure. So, obviously, your cost will be 1000, okay, will be 1000, and if suppose there is you do not place any order and there will be there are 2 failures, obviously, you need to purchase immediately 2 compressors with the total cost 2000, and similarly, if there is a 3 failures, the total cost is 3000. So, we follow this logic, but suppose you have just purchased 1 compressor. So, you have spent right now $1000, but there is no failure. Okay. If it is so, if it is 1 failure, you have already won. So, the cost will be $100, but if it is the 2 failures, already you have spent 100, and for the second one immediately you have to purchase 1 more compressor. So, the total value will be 100 plus 1000, $1100, and similarly if there are 3 failures. So, the 2 more compressors you have to purchase with the cost of say 2000. So, 2000 plus 100 already you have spent. So, it is 2100. So, similarly for this third strategy, that means ordering for 2 compressors. So, it will be $200 against 0 failure, against 1 failure again 200, against 2 failures 200, and if there are 3 failures, that means 1 more compressor you have to purchase with a price of $1000. So, the total the money spent will be $1200, and if there is a ordering for 3 compressors. So, already you spend you have purchased 3 compressors. So, irrespective of the number of failures from 0 to 3, the cost will remain same, that is 300, 300, for the third one 300, and for the fourth one again it will be 300. So, this is the total cost matrix we have developed, and then what you do against each ordering strategy, you calculate the expected costs. So, obviously, if the ordering strategy is 0, the expected cost will be 0 into say 0.3, that means 1000 into 0.4 plus 2000 into 0.25 plus 3000 into 0.05. So, if you add them, you will get a value of 1050. Similarly, for the other 3 strategies following the same rule, you calculate the expected cost. So, against ordering strategy 1, the expected cost is 450, against ordering strategy 2, the expected cost is 250, and against ordering strategy 3, the expected cost is 300. So, these are the 4 expected cost values, and out of these 4, which one is the minimum? Minimum is obviously 250. So, against 250 your ordering strategy is 2. So, that is the solution. Okay. So, this way you get a solution. Now, the cost matrix if you form, you get the solution when the probability values are known. And an easier method to obtain the same solution is the expected value approach. Already we have explained what is that expected the value, that means the probability of going out of stock. So, you have the expression for optimum probability of stock out probability, optimum stock out probability, that is given as PS, and this value is P minus V divided by A minus V. So, this is the purchase price P and V is assumed to be 0 in this case. This is the stock out, that means the demand is occurring, but you do not have at that point in time when the demand occurs, when the failure takes place, there is no stock of the compressor. So, immediately you have to purchase, and that purchase price is $1,000. So, obviously it is 100 minus 0 divided by 1000 minus 0. So, this value is the optimal stock out probability, that value is 0.10. From the given table, there are 2 failures associated with 0.05 stock out probability and 1 failure with 0.3 probability. So, 2 compressor should be purchased. Okay. So, that's we have already already we have mentioned that the solution is 2 out of this cost matrix, but an easier solution approach is, why don't you get the value of optimal the stock out probability and you refer to the probability distribution table in empirical form and you get the solution. Okay. So, now the second part is that the second part of this numerical problem is related to the holding cost assumed to be 10%. Okay. So, in case of a holding cost of 10%, the manager must correct his matrix cost, that means the cost matrix, according to the time value of money. So, the consulting a present value table for future single payments results in factors shown in the following table. Okay. So, what you try to do, that means you have to refer to this, that means suppose the failure at the end of year, that means there could be say 3 failures, 4 failures, 6 failures, 8 failures, no, failure occurring at the 3rd year ending, 4th year ending, 6th year ending, 8th year ending, 9th year ending. Okay. So, if so there could be different occasions, there could be 1 failure, there could be 2 failures, there could be 3 failures. Okay. So, if suppose there are 3 failures, so what we will assume that at the end of 3rd year there will be first failure, at the end of 6th year there will be second failure, at the end of 9th year there will be 3rd failure. Similarly, if there are 2 failures, we will assume that given the lifespan of the compressor 12 years. So, that means if there are 2 failures, at the end of 4th year there will be first failure and at the end of 8th year there will be the second failure. And if suppose there is just 1 failure within a time period of 12 years, we will assume that this failure will occur at the end of 6th year. So, now with the 10% holding cost, that means at that point in time, suppose at the end of 3rd year you need to purchase 1 compressor with the say $1,000 obviously. Now, obviously its present value you should calculate, that means as of now. So, this value will be 1000 into 0.751. Similarly, suppose at the end of the 4th year you need to say the purchase a compressor with a value of $1,000. So, what is its present value? So, for present value computation, what you need to do? You need to use this particular factor, that is 0.683 into 1000. Okay. So, the same rule will follow for failures occurring at different time periods. Okay. So, I will just explain the steps which we are following. A payment that must be made in future must be multiplied by the respective time correction factors. So, already in the previous table this time correction factor is given. The cost matrix is shown in another table. So, this is the cost matrix we are showing. For strategy 0, the cost for state of nature 1, okay, that I have already mentioned, that means 0.64 into 1000. Now, this 0.64, that means at the end of the 6th year, so we have this value, that is 0.564. So, if there is one failure, we are assuming that it will fail at the end of 6th year. So, this factor you need to consider. That means at that point in time, at the end of the 6th year, so you have to purchase a compressor with a price of 1000. So, its present value will be 1000 into 0.564. The cost for nature 2 is 0.683 1000, that is at the end of 3rd year, and this is at the end of this is at the end of 4th year, and this is then at the end of say the 8th year. This corresponding value is 0.683 into 1000, that is the first say the compressor you need to purchase, and this is the second compressor you have to purchase with the price of 1000 at the end of 8th year. So, corresponding factor is 0.67. So, the total value is 1150. So, the same logic we follow for calculating the cost against say the state of nature 3, that is 0.751 into 1000 plus 0.564 into 1000, 0.424 into 1000, that is 1739. The cost of each strategy is obtained in a similar manner. Since strategy 2 results in the lowest expected cost, the manager should order 2 spare compressors at the present time. That means there are 4 possibilities. That means ordering quantity could be 0 or 1 or 2 or 3. So, against 0, that means if suppose failure is 0, that means this is 0. If it is 1, that means at the end of so the 6th year it fails. So, corresponding cost is 564, and if there are 2 failures, that means obviously 1150, already it is clear. If there are 3 failures, that means the value will be 1739. Okay. So, the same logic we will apply. Suppose ordering strategy is 1, so this is 100, this is 100 against failure 1, against 2 it will be 567. Is it okay? So, 100 plus the second failure, that means just one failure has occurred, that means this is say the 567 and this is 1088. So, same logic you follow, you will get the answers. Okay. So, there will be 2 failures. So, the one failure occurring at this one 564. So, this is 564 and so this is 567 1088. So, like this you calculate, like 624 you calculate, that means third failure is occurring. Okay. So, accordingly you calculate what is the corresponding value. So, 624, that is 221.20 the expected cost against ordering strategy of 2. Okay. So, again we know what is the solution when the inventory carrying cost is assumed to be 10%. So, I suggest that you follow all the steps meticulously, so that you understand the logic fully. Now, just before I close, I will just refer to the type 2 problem. As already we have mentioned that the type 2 problem is a situation where there is constant demand, demand does not change, it is known with certainty, whereas the lead time is a variable. So, in this case the demand for the given period is known with certainty, however, the lead time is a variable. Probability distribution of lead time is given. Okay. A lead time can be selected with a high probability of arrival of the order prior to demand. Is it okay? With stockouts allowed, order is to be placed prior to maximum possible lead time. Okay. With demand remaining same, that means demand, say for example, demand of steel girders for building construction. A late delivery delays the activity. Is it okay? So, there are several cases. So, this is just one example. Like, so the Technology Club plans to sell Christmas trees during the Christmas season. Orders for the trees are to be delivered in specified dates, starting with earliest lot on 1st December. When should the order be placed if an 85% chance of trees arriving on time is desired? So, this is given 85% chance. The lead time distribution is given in the following table. So, these are the possible lead times, that means from 10 days to 16 days, corresponding the number of occurrences are given. That means the corresponding the frequency distribution table, and assume it to be assumed to be the probability distribution are given, and this is the solution. To satisfy all demand, the largest lead time of 16 days would be selected, as the trees would be ordered 16 days prior to the 1st December. That means there will be no stock out situation. However, from the table it is seen that 85% chance of trees arriving on time is desired. The lead time must be 14 days. So 85% of the chance there will be no you will get the item on time. Okay. So in this case the trees should be ordered 14 days prior to December 1 with 85% chance of arrival. So, this is the solution. That means we have just added one more column over here, probability of lead time less than equals to L. So, if the probability for 10 days lead time is 0.10, this will be 0.1, against 11 it will be 0.20. So, this way you calculate. So, when it is 14 days lead time, so the probability of lead time less than equals to L will be 0.85. So, this is the solution. Okay. So, these are the reference textbooks. Thank you.